It is water soluble. Ferric hydroxide is water insoluble. So when I treat it with water, I will have sodium aluminate in water and I will add sodium hydroxide as well. Because I'm hitting at high temperature, high pressure with excess of sodium hydroxide. So the aluminium present in the form of aluminium oxide in the bauxite will dissolve in sodium hydroxide to form sodium aluminate, which is water soluble. And ferric hydroxide is a reddish brown. It's a reddish brown precipitate, which is water insoluble. So when I treat it with water, the sodium aluminate will come into the aqueous solution and ferric hydroxide will remain as a residue. Along with sodium aluminate, sodium hydroxide will also come because sodium hydroxide is soluble in water. Now when I pass carbon dioxide at 50 degrees Celsius, sodium aluminate will convert into aluminium hydroxide and sodium carbonate will form. Aluminium hydroxide is a precipitate, white precipitate. Sodium carbonate is soluble in water. So when I filter, I will get aluminium hydroxide as a residue and sodium carbonate will be in the aqueous solution. When I heat it to 1500 degrees Celsius, I get Al2O3 pure, free from iron impurity. Okay?
Yes, yes.
In the Hulse process, what you do is, instead of sodium hydroxide, you mix with sodium carbonate and heat it to a high temperature. You will have sodium aluminate. Aluminium oxide will convert into sodium aluminate. Carbon dioxide will be evolved and ferric oxide will remain as ferric oxide. Ferric oxide is water insoluble. It's a reddish brown solid. Sodium aluminate is water soluble. The same reaction goes. So the only part which differs, in Bayer's process you use sodium hydroxide at high temperature, high pressure. In the Hulse process you use sodium carbonate at atmospheric pressure at high temperature. And you get carbon dioxide as one of the products. And sodium aluminate and ferric oxide will be the other two products.
Yes, sir.
When silica is a major impurity, it is called Sarpex process. You heat it in an electric furnace at 1800 degrees Celsius containing bauxite, carbon and past nitrogen gas. So when I heat it, the water molecule which were there associated with bauxite will go out in the form of steam. Aluminium oxide will be reduced by carbon to form aluminium, metal and carbon monoxide. The nitrogen molecule will dissociate at high temperature to nitrogen atoms. And aluminium reacts with nitrogen atoms to form aluminium nitride and ionic nitride. Ionic nitride, how do I know that it's ionic nitride? Because ionic nitride on reaction with water gives you aluminium hydroxide and ammonia gas. You see, aluminium nitride, the aluminium is 3 plus, nitride is 3 minus. 3 moles of water gives me 3H plus 3OH minus. N3 minus plus 3H plus gives me ammonia. And aluminium 3 plus 3 hydroxide ion gives me aluminium hydroxide. Silica get reduced by carbon to form silicon plus carbon monoxide, which goes out in the form of gas, and the silicon goes out in the form of vapor, silicon vapor, at high temperature 1800 degrees Celsius. So it also escaped from the system in the form of gas. So the aluminium hydroxide is free from silicon dioxide as an impurity. Aluminium hydroxide, when I heat it to 1500 degrees Celsius, I get pure Al2O3. So now aluminum is no longer associated with silicon dioxide. So I get, a bias process, Hall's process, and Surfax process removes ferric oxide and silica as a major impurity. Now alumina, you mix with a little bit of calcium fluoride, small amount. And electrolyze it at 950 degrees Celsius. You get aluminium at the cathode and oxygen at the anode. And along with oxygen, some amount of fluorine is also evolved at the anode. Cathode is your iron or steel, and anode is graphite. And graphite reacts with oxygen to form carbon dioxide. Carbon reacts with fluorine to form fluorocarbons. So the graphite is attacked by oxygen as well as by fluorine, which evolves at the anode. So it is to be replaced, the graphite rod to be replaced periodically. That's what is the preparation of aluminium. Aluminium, when you heat it at high temperature, you get Al2O3, or aluminium hydroxide, when you heat it to 1200 degrees Celsius, you get, or 1200 to 1500 degrees Celsius, you get aluminium. There are two types of aluminium. One is called alpha alumina, that is corundum. Another is called gamma alumina, which is prepared from gypsite. Gypsite is your alumina plus 3 water is called gypsite. When you heat it to 450 degrees, it changes to gamma alumina. Alpha alumina is the most stable form of aluminum oxide. So when you heat gamma alumina to high temperature, it will change to alpha alumina. Alpha alumina, they give rise to a species called emery. Alpha alumina with iron and sand as impurity is called emery. And you know what is emery?
No, sir.
You know.
Yes.
So the sandpaper is nothing but emery paper. And emery is nothing but alpha alumina with iron and silica as impurity. Okay. Alpha alumina is used for making synthetic gems. Aluminum oxide is white. Aluminum oxide, when you add few drops of chromic solution, chromium 3 solution, which is green in color, when you heat it, the entire mass changes to red. And since ruby is red in color, so it is called synthetic ruby. If I add few drops of titanium 4 and few drops of ferric or ferrous solution and heat it, the entire mass changes to blue color. And the sapphire is blue, so it is called synthetic sapphire. If I add vanadium 3 salt solution, same alpha alumina, I am adding few drops of vanadium 3 solution and heat it, I get the entire mass changes to green. Emerald is green. So the natural emerald is green, so you get the green color, so it is synthetic emerald. So you see how one can make gems, synthetic gems, from aluminum oxide by adding a few drops of transition metal salt solution.
Yes.
Aluminum oxide is cheap, and we can make synthetic gems by adding few drops of the transition metal salt solution. When I add chromium 3, I get red. When I add titanium 4 and iron 3 or 2 plus, I get blue. When I add vanadium 3 plus, I get green. When I add ferric plus, I get yellow. Gamma alumina is used as chromatographic adsorbent material. What is meant by chromatographic adsorbent material is that you take a glass tube and fill with gamma alumina. So you pour through filled funnel, make a suspension of gamma alumina in water and put through funnel. The column is at the end of the funnel, at the end of the tube you have glass wool, which will allow the water molecule to pass through, and the column will be packed with gamma alumina. Now if I have a mixture of organic compounds with different polarity, I can separate them very easily. The greater the polarity or higher the polarity, longer is the retention time on the column bed. So the species which has the highest polarity will be attracted by gamma alumina most strongly, so it will remain on the column bed for most of the time, for a longest period of time. And the one which has the lowest polarity will come out first. So in this way, I can separate the mixture of organic compounds with different polarity. Okay, so if I have, suppose I have a mixture of orthodichlorobenzene and paradichlorobenzene. This will not have a dipole moment, but this will have. So it will remain on the column bed for a longer period, and this will come out first. So this is the material which is used to separate the mixtures of organic compounds having different polarities. They are called adsorbent material, chromatographic adsorbent material. And gamma alumina is used as an adsorbent material. I can make aluminum chloride from alumina like Sarpek's process. Alumina plus carbon plus chlorine. Instead of nitrogen, I have used chlorine here. Carbon reduces alumina to aluminium metal. Aluminium metal gets oxidized by chlorine to aluminium chloride.
Yes, sir.
Yes, sir.
Or I can take aluminium and react with chlorine, heat it, I get aluminium chloride. But if I put aluminium chloride in the solid state is not AlCl3. In the solid state it exists as Al2Cl6. It is a dimer, not a monomer. These chlorine are forming two centered two electron bonds, a normal covalent bond. But these two chlorines, they are forming a covalent bond and a coordinate bond.
Yes, sir.
So the aluminium is tetrahedral. Each aluminium is tetrahedral in Al2Cl6. It is not trigonal planar. It is tetrahedral because there are 4 chlorines surrounding aluminium. But if I heat it to 750 degrees Celsius, then I get a vapor of aluminium chloride. And now it is trigonal planar. Because aluminium has the outermost electronic configuration is S2P1.
Yes.
Now, since aluminium forms 3 covalent bonds, so I require 3 unpaired electrons. How do I get 3 unpaired electrons? This changes to, just like carbon changes to sp3,
Yes.
S2P2 changes to S1P3, so it gives you sp3 hybridization. Similarly here, aluminium gives you sp2 hybridization. But only in the vapor phase, not in the solid. In the solid it exists as a dimer. Only when you heat it at a very high temperature, you get a monomer. When I dissolve it in water, I get an aqueous solution of aluminium chloride. And when I crystallize by evaporation, I get aluminium chloride 6 water as a white crystal. And this crystal, this has a structure. The 6 water molecules are forming a coordinate bond with aluminium, and 3 chlorides is in the ionization sphere. So 6 water molecule is in the coordination sphere. They are not lattice water. They are not water of crystallization. They are coordinated water. Alums. Alums are double salts.
Yes.
We have discussed alums when discussing double salt versus coordination compounds.
Yes.
There are 3 types of alums: potash alum, chrome alum, and ferric alum.
Yes.
Now, magnesium we have to do. Okay, magnesium. The source of magnesium, dolomite. There is calcium carbonate, magnesium carbonate, magnesite. That is magnesium carbonate. Carnallite. That is KCl magnesium chloride, 6 water. And so, one of the methods of preparing magnesium is from dolomite. And this method from dolomite is known as Fijian's process. When you heat calcium carbonate, magnesium carbonate, and another source of this when you reduce with ferrosilicon alloy, that is iron stroke silicon. 2 moles of calcium oxide dot magnesium oxide plus iron ferrosilicon gives you magnesium, calcium, orthosilicate and iron. So the silicon, which is in the zero oxidation state, is reducing magnesium 2 plus to 0. And silicon is getting oxidized to silicon 4 plus. Because you can see 4 into 2 is 8 negative charge, 2 calcium is 4 positive charge, so the silicon has to be 4 positive.
Yes.
So silicon is reacting as a reducing agent to reduce magnesium oxide to magnesium metal and getting oxidized to silicate ion. And calcium binds with silicate ion to form calcium silicate, orthosilicate. The other process is from seawater.
Excuse me, sir.
Here.
Sir, cannot we know the variability in in the melting points of CaCO3 and MgCO3 and hence separate them?
What?
If we heat them at different temperatures, means they can have their different melting points. So at one temperature, a single one of them will get melted and the other can be separated. Why isn't that possible?
How does it help you?
So if we keep rising the means since these two exist as independent compounds also, it can be possible that if we keep increasing the temperature at a certain limit, the one with the lower melting point will start melting, and up till a certain limit it will be completely melted. So the one in solid form can be extracted from the liquid.
But that will be the oxide, not the metal. Carbonate on heating, does it give metal or metal oxide?
Oxide.
Seawater contains magnesium salts. If I take seawater in a bucket, a large bucket, and evaporate, the water will go out in the form of steam, and I will get a concentrated solution of magnesium salts. When I add calcium hydroxide, I get magnesium hydroxide precipitated and calcium salts like chloride will be soluble in water. So I filter magnesium hydroxide from calcium chloride.
Yes.
Yes, sir.
Magnesium hydroxide I dissolve it in HCl. So get magnesium chloride and dilute HCl. So I get an aqueous solution of magnesium chloride with HCl. When I evaporate, I get magnesium chloride hexahydrate. A white crystals of magnesium chloride hexahydrate. I pass dry HCl gas. Dry HCl gas absorbs water molecule and converts into anhydrous magnesium chloride. Because if water is there, if I electrolyze, I will get magnesium oxide and not magnesium metal.
Yes.
Now I mix with sodium chloride and calcium chloride and electrolyze it with iron pot as cathode and graphite as anode. And temperature I use at 750 degrees Celsius. I get magnesium at the cathode and chlorine at the anode. And that is how you can prepare magnesium from seawater. And that is called Dow's process. So the Dow's process involves magnesium from seawater, where magnesium is present in the form of magnesium chloride. I concentrate by heating so that the water goes out in the form of steam. The magnesium chloride concentration increases. When it is sufficiently concentrated, I add calcium hydroxide, lime water. Magnesium hydroxide is more insoluble than calcium hydroxide, so magnesium hydroxide gets precipitated and calcium chloride goes into the aqueous solution. I filter off the magnesium hydroxide precipitate, dissolve magnesium hydroxide precipitate in HCl, I get magnesium chloride, which is water soluble. When I evaporate, I get a magnesium chloride hexahydrate. Unless I remove the water of crystallization, I cannot electrolyze it, because otherwise, at high temperature, magnesium chloride will undergo hydrolysis to form magnesium hydroxide, and magnesium hydroxide will further dehydrate to give magnesium oxide. So I will not get magnesium metal, but I will get magnesium oxide. So first I have to remove water molecule by passing dry HCl gas, which will absorb the moisture and convert the hexahydrate magnesium chloride hexahydrate into anhydrous magnesium chloride. Now I mix magnesium chloride with sodium chloride and calcium chloride, and the mixture melts at a lower temperature than magnesium chloride. So if I electrolyze at 750 degrees Celsius using iron as cathode, graphite as anode, then I get magnesium at the cathode and chlorine at the anode. And that is how the magnesium can be prepared. Duralumin, aluminum, write down some alloys of aluminum. It is copper plus aluminum. Alnico